Welcome to today's session. We are going to discuss the concept of analog to digital converter in today's session, and that is an overall in the overall system, that is an important part. That is the last part in our analog signal processing chain. So, let us look at the system with which we began our discussion. We have the front end amplifier, for which we have already had detailed discussion, which is acquiring the data from the sensor, and we have seen the design issues associated with the front end amplifier, starting from high level specification, going down to the blocks and the circuit level specification, transistor level design, sizing, addressing different issues starting from noise, bandwidth, gain, linearity, precision, and so on. Likewise, we have discussion on the low pass filter, the anti-aliasing filter, which is supposed to reject high frequency noise, and there we saw that we can use some special techniques like GMC filter for implementing very low frequency cutoffs. And finally, we have the processed amplified filtered signal, which is going to the A to D converter over here. And next it goes to the digital domain, and you can do all your signal processing in the digital domain, the digital signal processing that you want to do. You can also store your data in the digital memory conveniently. So, this is the overall system, and we have looked into the details of the first two, and we are going to start with the implementation of the ADC. So, we will first discuss the basic concepts of ADC. Many of the specifications of the ADC we will skip at this point, because the purpose of this course is to give you a design example. So, some of the definitions of specifications of ADC will be skipping those in favor of time, and we will be looking at the circuit implementation of relatively simple topology. We will try to start from high level specification of the ADC and its building blocks given the signal conditions, and then we will be going into the design issues, transistor level, block level design issues, dealing with the intricacies and the non-agilities at transistor level design of each of those blocks. So, that is going to be the approach. So, let us start with the high level description of the A to D operation that we are going to have on our signal. So, first of all, regarding the swing, we have already discussed that the overall amplification and filtering stage is supposed to give an overall gain such that the weak signal over here is sufficiently amplified and it is mapped to the input dynamic range of the ADC. What is the input dynamic range of the ADC? That is basically the maximum peak to peak signal swing that the A to D converter can process. And in order to take advantage of the maximum dynamic range, we always try that the signal coming after the analog processing is almost its peak to peak range is almost matched to the input dynamic range of the ADC. Now, to do that, we have also seen what are the steps to be taken in the front end amplifier. Generally, the front end amplifier is composed of at least two stages, where you have the low noise amplifier at the first stage, where the noise consideration is very important, and the second one is a variable gain amplifier or a VGA. I can call this a low noise front end amplifier, and second one is the variable gain amplifier. So, depending upon the current signal magnitude, I can change the gain of the variable gain amplifier. We have seen how to program the gain of a VGA using programmable capacitive banks. Depending upon the signal magnitude at a particular time, the DSP can send some feedback signal to the VGA, some digital control signal to the VGA, and adjust its gain, so that at any time the signal amplitude is say reducing, the VGA gain will be increased, and vice versa. So, that the overall magnitude of the signal coming over here is mapped to the input dynamic range of the ADC. What we have seen in our previous examples is that the VGA over here is capable of giving us almost full swing, and for a 2 volt supply, the swing can be almost close to 0 to VDD, and in general it may be beneficial to apply the VGA after the filter, so that the circuits implementing the filter did not suffer from excessive nonlinearity, because if you give a fully amplified signal to the filter, full input swing to the filter, that can introduce a lot of distortion and nonlinearity in the filter itself. So, a better technique would be to interpose the filter between the low noise front end amplifier and the VGA, so that after the filter you can use the VGA and obtain a full swing signal which is going to the ADC. That is another concept we have seen, and now once we have this signal traversing this entire front end, and after being processed and amplified it is available at the ADC, we are expecting that the swing of the signal over here is almost from 0 to VDD, and therefore, the ADC over here is also supposed to accept that entire signal. What is the basic function of an ADC? It is supposed to quantize a continuous time, continuous amplitude signal into n number of discrete levels. So, it is supposed to quantize the entire input signal into n discrete levels, and generate a digital word which depicts the signal level with respect to the scale. For example, if we have say almost close to 2 volt peak to peak signal, and we want a 7-bit ADC for instance. So, we have been talking about the resolution, and in the very beginning we have said that let us have at least 1% precision for the signal processing in the analog front end, so that close to 7-bit precision can be maintained. So, suppose we are going for 7-bit ADC, and therefore, we are going to have 127 different levels over here, or 127 different comparison levels over here. So, if I look at the individual section, the difference between the two levels is going to be around 2 volt upon 127, comes around 15 millivolt. So, basically this entire signal, which can range from 0 to 2 volt, is divided into these 15 millivolt segments, and the ADC is supposed to figure out that the current sample, where is the current sample located in this entire range, and corresponding to that it is supposed to generate a digital word which encodes these 127 levels. So, we know that for 127 we need 7-bit digital word. If the data is lower than the lowest reference, then you can say that all the 7 bits will be 0, and if it is higher than the highest reference, then all the 7 bits will be 1, and in between we can accordingly have the corresponding analog value converted into the digital form. So, what is the simplest way in which this can be done? If we just logically think of the overall operation, overall functionality that we are trying to achieve, the simplest operation is that you compare the input signal with these thresholds starting from 15 millivolt, 30 millivolt, 45 millivolt and so on, and then determine what is the level of the signal with respect to all these thresholds. So, I can have a bank of comparators, an analog comparator. If I talk about an ideal analog comparator, its operation is well understood. If there is a reference signal and you are having an input signal coming over here, and suppose you have a reference signal coming at the negative terminal of the comparator, if the signal is higher than the reference signal, the output should be going high. A comparator is having only 2 output levels, it can be either high or low. So, generally if you are having an analog circuitry implementing a comparator, the high level corresponds to the supply, which can be VDD, and the low level is the 0 or the ground supply. So, these are the 2 possible levels for an ideal comparator, high or low. Input can be analog, you have a reference which is a fixed value with which you are trying to compare the input, and if the input is higher than the reference, output will be VDD, and if it is lower than the reference, output will be 0. That is the function of a comparator. So, in order to implement this quantization, this simple quantization, I can imagine having a bunch of comparators which are all receiving the input signals on their positive terminal, and they are having reference signals, reference voltages applied to the negative terminals. So, suppose this is my first comparator C1, this is C2, this is C3, and likewise you have Cn, and in order to have 7 bit quantization, we will require 127 different comparators, so that it can decide which of the 128 levels of data is allocated to. So, here I can have the vref. If I call this the lowest, the difference between the reference level, if I call this delta, the lowest level over here will be delta, which is 15 millivolt. This will be 2 delta, 3 delta, and so on. And here if I call this n minus 1 delta, then I can say that if the input signal is coming over here and these are the outputs of this comparator, if the input signal is lower than the delta, that is the lowest reference point, all the bits will be 0 and all the comparators outputs will be 0, because in that case the signal coming at the positive terminals for all the comparator, it is lower than the references. So, we will get straight 0 outputs over here, and as the signal goes up, suppose it is higher than 2 delta, but lower than 3 delta, in that case we will have the first two comparator giving us 0 0, whereas since it is lower than 3 delta, I will have I am sorry, I will be getting 1 and 1 at the output of the two comparator. If the signal is higher than 2 delta and other two comparators, all the other comparators will be giving us 0 0, and likewise suppose the signal is higher than even 3 delta, then I have 1 1 1, but if it is lower than 4 delta, so the fourth comparator onwards all the values will be 0. So, basically as the signal goes up, we are having some kind of thermometer code where the lower comparators outputs are going to be set to 1 and the upper comparators there will be 0, and if the signal amplitude increases, larger number of comparators from the bottom point will be having output 1 and smaller numbers will be having output 0. So, the number of comparators having high output basically denote the signal level. If larger number of comparators starting from the lowest one are having ones, that means the signal is towards the higher value, and the extreme cases when the signal is, as I said, very close to the or even higher than the uppermost threshold, which is n minus 1 delta. So, in that case all the comparators will have output 1. So, it is some kind of thermometer code that we are seeing. As the signal goes on increasing, the number of 1 goes on climbing. So, we can see that this is the mercury of the thermometer. So, 1 can be seen as the mercury of the thermometer. The high output coming from the comparators can be seen as the mercury level in our thermometer code. As the signal is increasing, the number of 1s is increasing, or in other words, the number of comparator going high is increasing. And of course, this is not the binary code, this is a thermometer code, and therefore, from here we need an encoder which can convert this into our binary code, 7-bit binary code, and for that we need to just look at the corresponding truth table and arrive at the digital logic. So, rather than going into detail, we can just say that there is going to be an encoder which is basically taking in these n minus 1 inputs. So, you have outputs starting from C1 to Cn minus 1. So, these are Cn minus 1 inputs coming in, and there is a digital encoder logic, which is supposed to provide us our desired 7 bits, you can call it D1 to D7, corresponding to this n minus 1 inputs. So, basically we can write truth table for each of these outputs, each of these 7 outputs as a function of these n minus 1 inputs, and then simplify the logic function and arrive at the logic implementation of the individual outputs. That can be done using a K-map, and a computer can solve it because you have such a large dimension of inputs. So, CAD tools can solve this truth table and give us an optimized Boolean logic, gate level logic implementation of this digital logic function, where you have n minus 1 input and each of them can be 1 or 0, and you have corresponding to that 7 outputs. Each of these 7 outputs are some logic functions of these n minus 1 inputs, which can be obtained using CAD tool. All you need to do is specify a truth table where each of these output, the 7-bit outputs, will be specified as a function of these. So, this is simplest possible logical implementation of an A to D converter, where we are using analog blocks, namely the comparators, and after that the digital outputs obtained are encoded with the help of a digital logic. And here we can see, of course, that if you want higher resolution of the ADC, that means you want larger number of bits in your ADC, then of course the number of comparators required will go on increasing exponentially. For 7 bit it is 127 ADCs, for 8 bit it will be 255, sorry, for 7 bit it is 127 comparators, for 8 bit will be 255 comparators, and so on. So the number of comparators required will go on increasing steeply as the number of bits increase. And in general, the flash ADC topologies are not implemented for more than 5 to 6 bits. Beyond 6 bit it becomes very costly in terms of number of comparators that are required. So if the resolution required is less than say 6 bit, then we can still go for flash ADC. And one of the advantages of the flash ADC that it is very fast. In one shot it can give you the desired binary codes. The input comes over here, and immediately you have the entire 7 bit available at the output of an encoder in single cycle. So it can be very fast, but of course you have larger number of comparators implementing it, and exponentially it goes on the number of comparators, and hence the area goes on increasing exponentially. So we can have relatively simpler versions, alternate versions, where we can mitigate this disadvantage and use fewer number of comparators to implement our overall functionality. And we are going to look into one such topology which is going to be highly suitable for the signal processing we are trying to do, and specifically the kind of signal characteristic that we have. Of course, the choice of ADC is very much dependent upon the signal characteristics. If your signal is having a relatively high frequency content, then of course you will try to choose ADCs which can process the signal faster and give you the digital output faster. If the signal content, the frequency content of the signal is relatively low, I do not worry so much about the sampling speed or the conversion rate of the ADC. In some applications, you may require very high resolution of ADC. We are all aware of the standards of imaging, for example, audio, where people may go for 16 bit, 24 bits of data, and there of course we may not be at all choosing simpler topologies like the flash ADC. So there the more important concern would be the resolution, and there we may need to go for ADCs which require much higher, which can give us much higher resolution. And again, there are some applications where both resolution as well as speed becomes important, and those kind of ADCs become more and more challenging to design. So here in our case, we are looking at a biomedical signal which is relatively low frequency signal, and also an application which is having moderate resolution. We may be able to do the required processing with just 7 bit of resolution, that is moderate or relatively low resolution. You can have applications where just 4 bit may be sufficient. In this application, we are looking at neural signal acquisition and processing. People have shown that 7 to 8 bit of precision may be good enough for extracting the required information in the digital domain. So the target of the ADC resolution comes from the data processing requirement. So if you are running some algorithm or trying to implement some algorithm in the digital domain, that will tell you how much bit of precision ADC must have, so that correspondingly how much resolution, how much accuracy the analog domain processing must preserve, so that the required information can be extracted in the digital domain. So that information is coming from some established studies which are telling us that okay, 7 bit of precision is good enough for the data that we are targeting, and then we also know the kind of frequency content that we have in our data. So starting from this high level requirement, the data rate and the corresponding resolution, we are going to arrive at the ADC topology. We are first of all going to choose an ADC topology which is suitable for this particular signal, and then we are going to look into the block level implementation of that ADC, trying to arrive at the specifications of those ADC, then go deeper step by step and deal with the intricacies of the blocks and the circuit level implementation. So let us look at an alternate scheme that we are going to focus on and study in deep, that is called single slope ADC, a relatively simple architecture, but it is a good enough case study through which we can show a lot of delicate details related to the circuit level implementation of the ADC. So the single slope ADC is just the flip case of a flash ADC, where rather than having n number of comparators and so many different references, we have just one reference which is being swept. So, in the single slope ADC, we have only one comparator, and rather than comparing the input signal with so many different levels, we compare it with a changing reference, linearly increasing reference. So, the overall scheme for such an ADC can be represented as block level. So, you have first of all the input signal coming say at the negative positive terminal of the comparator, and you have the Vref which is increasing linearly, and you have the comparator output which is supposed to detect the crossing point when the Vref basically approaches or crosses V in. So, Vref is supposed to start from 0 if your lower supply is 0, it is supposed to start from 0, that is the minimum input level possible that the ADC can achieve or receive, and it is supposed to increase linearly with time. So, the Vref is supposed to go on increasing with a constant slope ideally, and we are interested in finding out the time at which Vref crosses the V in. So, if the V in is larger, then of course, Vref will take longer time to reach V in. If I say that this is your V in 2 and this is V in 1, if V in 2 is greater than V in 1, then of course, we can see that if I assume that the slope of the Vref is constant, the T2 will be linearly related to T1, and as V in goes on increasing, we will have T2 proportionally increasing, exactly proportionally increasing with respect to V in. So, T2 will have exact proportionality with V in, and as a result the T2 or basically the time of the comparator flipping captures the magnitude of the input signal. If the input signal is larger, the time of the comparator flipping will also be proportionally larger, exactly proportionally larger. So, it is basically capturing the magnitude of the input signal. So, all we have to detect is that if the comparator has been say initialized with 0, initially when the Vref is 0 and V in is of course higher than that minimum value delta V or higher than 0, then of course, according to that the comparator output will be high to begin with, and then as the Vref goes on increasing, ramping, ultimately at some time t the output over here will be going low, and that time t is the measure of the digital value, the analog value. And how do we measure time? One of the most convenient way is to use a counter. So, you can have a digital counter which is having some particular clock given to it, and the enable signal is coming from the comparator. So, you are having an enable signal which is basically the comparator output, and whenever the comparator output is falling low, the counter stops counting. So, it has to be initialized with say a 0 count. So, there should be a reset input, so that at the initial phase of the comparison, when the comparison is starting, the counter output are all set to 0. So, in our case, we are expecting that we are going to have 7-bit counter, because we need 7-bit word for the analog value. Initially, it should be starting with all 0, and the clock should continuously increment the counter output from all 0 towards the maximum value, which is 1 1 1 all ones, and the counter has to stop whenever the input signal reaches the reference signal, and that particular count produced by the counter at that time is basically going to quantize the total time taken by the ramping Vref to reach the input signal, and hence that digital word is going to be the quantized value corresponding to our input signal. So, that is a simple concept regarding single slope ADC, and then we can look into the overall implementation of this scheme. Now, so we will be proceeding step by step and going into the details of each of these blocks. So, let us start with the very first block, which is going to come before the comparator unit. So, that unit is called the sampling block. So, before the analog data can be digitized by our ADC, which can be basically denoted by this entire black box and its constituents, the data must be stable, it must be sampled and it must be at a constant value, because ultimately we are trying to digitize samples of the analog data. So, if you have a continuous time analog data coming in, we need to first of all in the time domain sample the continuous time data at specific instances and then obtain the digital value corresponding to these samples. And we know that the maximum sampling frequency is determined by the Nyquist rate. If we know the maximum frequency content of the signal, we can determine the sampling rate as 2 times that frequency, and that is going to give me the interval between the sampling points. And these are the analog values which are sampled, which are of our interest and which are going to be converted into the corresponding digital word representation. So, we will be looking into the details of the sampling unit over here, which although may look simple, but there are several design issues associated with the simplest block over here, which is a sample and hold circuitry, and we will be looking into the transistor level implementation, its related non-idealities, design issues associated with that, and so on. So, let us stop here before we go into the details of this sample and hold unit. Let us stop here and see whether there is any question.